Hello, everybody. Welcome back to the Twin Talks. For today's show, I'm your host, Samir Kher. I'm the Senior Director for R&D at Ansys. I head up our digital twin product area. And today, as you may have guessed, it is the final episode of season two. Throughout this season, we've explored how simulation, reduced order modeling, and digital twins particularly are reshaping our industry. And to close this season, I'm really thrilled to spotlight an application where digital twins are making a significant real world impact in conjunction with a customer of ours, and that's in the space of medium voltage drives. So joining me today is Bogdan Ionescu from Innomotics, a company that's leading the charge in advancing drive technology. Bogdan has been pioneering the integration of physics-based ROMs and hybrid digital twins directly into medium voltage drive controllers, enabling smarter thermal management, higher performance, and laying the foundation for AI-capable drive systems. We're going to discuss how medium voltage drives work, why thermal insights matter, how ROMs unlock new operating margins, and how Innomotics is preparing for the next generation of intelligent data-enhanced industrial systems. Bogdan, welcome to Twin Talks. It's great to have you with us. Could you start us off just by telling us a little bit about yourself and about Innomotics?
First of all, thank you for everybody attending this presentation. We are going to try to make it as informative as we can. I am a principal key expert working in the R&D department, specifically the power electronics group at Innomotics. And I'm in charge with electromagnetic-centric multiphysics and multi-domain simulations. As such, I'm doing a lot of standalone simulations. I'm using Maxwell, Twin Builder, CFX, Fluent, IcePack, sometimes mechanical modules. But sometimes I'm also doing combined simulations using different Ansys modules which are coupled in a workbench environment. For example, I will take an example of the analysis of the impact of short circuit in medium voltage drives. In this case, I'm using Maxwell to obtain power density, the force density distribution in the conductors of the drive, and then I couple that with the appropriate mechanical module to look at the stress and displacement of the conductors as the application requires. The other thing that I am doing, I'm providing guidance to colleagues who need it occasionally. And I'm also providing the management advice regarding simulation and also sometimes purchases of new software and hardware. And speaking of software, let me make here a mention. We chose Ansys a couple of decades ago when it was already clear to us that it will provide us the simulation platform that is going to fit our needs for simulation for the foreseeable future. And today I'm pretty happy to say that that assumption was correct, and we are very happy that at the time it was the right choice. It continues to be the right choice.
Excellent. Thank you so much. So tell us a little bit more about medium voltage drives. What are the main design constraints? What are some of the corner conditions? What limits medium voltage drive performance?
I look at it as an energy converter. It takes at the input a fixed voltage, medium voltage at fixed frequency, whatever is available at the location where we have the application, and it's converting that into a variable voltage and variable frequency electric energy. For example, let's say that the location of the application have 6 kilovolt grid, and you need to convert that to a 10 kilovolt, 10 megawatt available to an electric machine, electric motor. and the drive is doing that. Plus, it provides a digital control of a number of quantities of interest, such as current, torque, power, etc. And all that while providing dynamic control of things that are very important, like the startup of the drive, the acceleration, decelerations, things of that nature. So that's the main aspect. But I'd like to stress out another important one. In doing all that, the drive, our medium voltage drive, it's providing a minimum of disruptions to the grid. And that means that it absorbs from the grid an almost perfect sine wave. So you could look at that as the drive absorbing power on the fundamental frequency, be that 60 hertz or 50 hertz, and it's generating high order and low amplitude frequency, which is injecting into the grid. So this is the reason why it provides a minimum of disruptions to the network, and it absorbs an almost perfect sine wave. You may ask what happened to the other low order harmonics, which of course we all know those are the dangerous ones. Well, the drive has, as part of the drive, there is a power transformer, which is of a special design, such that all those low order harmonics, the dangerous ones, are totally eliminated by this special design of the power transformer. And this is the reason why this medium voltage drive is also known as the perfect harmony drive. And that's the other nice thing about it. This drive, I have to say, is very important to our business because it provides over 70% of the revenue to this medium voltage drives department, part of Innomotics.
Excellent. Okay, that's helpful. So, then in that context, can you sort of explain what types of reduced order models you use in your medium voltage drives, and what physical insights they provide, especially inside your transformers and other sort of critical equipment?
Yeah. Well, one of the aspects that are very important to control by the drive is the temperature of the silicon inside the power cells of the drive. As we know, electromagnetic fields, they have two important consequences. One, that they produce force, torque, but also they produce heat in the process of controlling the motor or the silicon inside the drive. Also, the power transformer, which is also a part of the system, they heat up. And that is one of the aspects that presents a corner situation, because in the process of designing, you have to make assumptions about the maximum operating conditions. And that is putting us into the situation of designing the device according to the worst case situation. But as a matter of fact, in the process of the application actually being active at the location chosen by the customer, situations can be different, and then we have to adapt to those conditions, whatever they could be. So one of the aspects that we control is the temperature, as I said, and by doing that, we have our ROMs that are actually mimicking the physical behavior. So we apply the power to the silicon devices as measured by the drive. So we have real-time power, we have real-time airflow. So we have perfect control of the power injected in the drive that produce those high temperatures, possibly, and also the cooling aspect. and then we take these parameters and we apply it to um, the controller, such that now the controller is in charge. So instead of assuming those operating conditions, it's adapting them. And by knowing exactly what are the critical temperatures inside the silicon, it can control effectively the drive, such that we can provide additional power if the application requires it, because now we know the actual temperatures without having to assume a lot of things.
Assume, yeah. Right. Okay, that makes a lot of sense. And sort of a related questions, right? Related question that comes up is, how do you make sure that the predictions that these ROMs make are accurate and reliable? How do you ensure that they actually mirror what you've seen in the CFD or as part of your prototyping?
Yeah, this is a very interesting thing that you are bringing up. First of all, in the process of designing the drive and the power cells and the transformer, there is an important part of lab testing of a prototype. So we always have a prototype which is built differently from the series of the drive that is actually being shipped to the customer, which means that we have multiple measuring points that we are taking into account, and we compare the predictions made by this ROM with the actual measurements taken at as many locations as possible, which will not be, of course, available when we ship the final product. So that is a part of the answer that I have for your question.
Yeah, that makes. Oh, go ahead, keep going. Sorry.
Yeah, the other thing is that each of these power cells, they have the IGBTs with one location where you can actually measure a temperature. So that location is actually duplicated in the ROM. So we always compare an actual measurement taken at a certain location designed for this purpose and compare it with the prediction. So putting this in sync makes sure that our application is functioning correctly, and the ROM is providing realistic results. With other words, we call this keeping the ROM honest. This is how we do it. So part is the prototyping phase. Second is even in the ship product, we have a way to monitor and compare measured and simulated temperatures.
Excellent. Okay. Yeah, that makes a lot of sense. We have other customers that use very similar methods as well. So that makes a lot of sense. You've sort of now addressed how these ROMs really help you make predictions, better inform the control. You've talked about how you're using various techniques to keep them accurate. Could you also maybe talk a little bit about, in addition to the ROM, are you incorporating measurement information into your ROM to create these hybrid models to get even more accuracy?
Yes, actually, a lot of the quantities are monitored by the drive and are provided to the ROM as real inputs. For example, the power injected into the IGBT comes from measurements of currents and voltages, and then we have a real power that we can process, and we make sure that the ROM is provided with an actual power being dissipated by the device. The other thing is we have a way that we can monitor the airflow. So real time, we can have these quantities being calculated and processed and provided to the ROM as actual quantities that the ROM can take and produce the temperature predictions that then we use to decide if we can in fact inject more power if the application requires it, or less power, or contrary, opposed to that, we can decide if there is not enough um, power loss in the drive. We can decide to lower the airflow uh, rate provided for cooling such that we diminish the noise, because you can imagine those megawatts of power, the blowers providing the cooling of the drive, they produce a lot of air, and that comes with significant noise.
Okay, excellent. Yeah, that helps. And then it's sort of going up a level of in terms of abstraction. Through the use of Ansys Twin Builder, how do you bring in addition to the thermal behavior and some of the other things you talked about, how do you tie different physical domains like the thermal domain, the electromagnetics, mechanical, to model your overall medium voltage drive?
Yeah. Well, we had for a long time an electromagnetic ROM that was capable of mimicking the electromagnetic behavior of the power cells and the drive as a whole. These are models that are, well, maybe 10, 15 years old, and they have been extremely useful, not only in providing the answers that the controller needs, but also helping us in the design process, because we look now at this application as blocks that we put together. We have the description of the drive. Part of that are this electrothermal and CFD behavior of the power cells, of the transformer. So we look as building blocks that we put together, and then in the design process we can do all kinds of what-if scenarios, depending on what we believe the market wants from us. And even before this new concept they get implemented, we can work in R&D to put all these pieces together, one model for the drive, and then inside that the power cells that are the key to the process of creating the medium voltage, also the power transformers, and using all kinds of different blocks, because we have now a library of such elements. We have a library of all the power cells, whether they are air-cooled or water-cooled, for higher power of the application, and also transformers. We have these models, and we put together, and it's kind of we could call it, like a Lego game that you could look at it that way. And you, by putting together all these building bricks, you can create scenarios that you can look at carefully and analyze what will happen even before you start planning the new drive series.
Yeah, excellent. I love that analogy to Lego building blocks and combining things to create a prototype of your overall system, and testing it out before you actually even have a physical prototype. So just in terms of maybe looking at overall, right, from your experience at Innomotics and in your current role, in your previous roles, what benefits do you see specifically for from using ROMs, from using these digital twin technologies, in terms of performance, flexibility, value? Like, what are some of the benefits that you see?
Well, the benefits, I think, are sizable. Aside from this, impact on the design process, which makes it, streamlined and very effective, I'm thinking of the benefits that you can bring to the customer. I believe that these ROMs will become even more important in the future by allowing us, the manufacturer of the drive, to get closer to the customer. So when we understand the customer's requirements and allowing him to take full advantage of the capabilities of the drives, that's when we think we are going to make an even bigger impact. I spoke about eliminating some of those corner conditions, but that is only part of the benefits we can bring. We have in plan to include in this ROM story the motors or the generator, let's call it the electric machine that is between the drive and driven mechanism, but also the driven mechanism that will be also part of what we could offer to the customer, so that when we give that to the customer, the whole control between the starting point where you have the initial energy or the initial parameters, and then you model the whole thing. You can have um, better answers for what the customer wants. For example, let's say that the driven mechanism can act with some uncontrolled vibrations. We can take that into account if the driven mechanism is part of the ROM, and we can describe that as a ROM. We can look at what are those eigenmodes that make those vibrations dangerous, and then we can look at our drives, because you have control on the harmonic content of the torque supplied to the motor. So by taking into account, for example, some vibration, unwanted vibration, and then going back to the drive, by changing the switching frequencies for the IGBTs, we control the frequencies, we control the shape of the currents and voltages supplied by the motor, and by that, we control the harmonic content of the torque curve, and therefore we can diminish and control the unwanted vibration. And this is something that has not been done before. And you can imagine how important it would be for the customer to have control over aspects that before he could not think of getting access to.
Yeah, excellent. Yeah, that's a really good example. And then maybe sort of related, as you think about things like predictive maintenance or identifying signs of issues in terms of cooling or aging, getting uptime, getting higher energy efficiency, and improving the quality of control, kind of taking these digital twin models for operations. Where do you see that, and do you see applications and customer interest in that space?
Samir, this is an excellent point. That is the other part that we are also doing. Obviously, the silicon devices, not only that, but also the capacitors, they go through an aging process in the drive, and some of these devices being critical for the operation, we take we take care and control of how high the temperature is getting, and we have inside the drive aging models for the IGBTs. We are looking at the temperature distribution, the temperature history, because unlike the temperature sensor that you have inside the IGBT, which gives you temperature at a certain location, now with these ROMs we have exact knowledge of the temperatures of all the silicon junctions. One IGBT contains, let's say, 6 or 10 or even 12 individual IGBTs, and we have actual information about each of those temperatures. And we have the ability to take all those and put those into our aging model, and then you can have answers that way. That is one way to look at it. The other thing, we are looking at these ROMs of being able to communicate with the cloud. Some of these quantities, they make a lot of sense to be supplied to the cloud. They do not make an impact immediately, so they do not need a real-time estimation, but providing all this stream of data to the cloud about all kinds of temperatures in the cloud, all these things they can process in a way that makes sense for providing maintenance information to the customer, but also to us as a drive manufacturer. And then we can learn from the process, and the customer can also learn what aspects become critical and when maybe a stop of the drive for maintenance purposes can prove beneficial, rather than pushing things too far and risking an outright failure.
Yeah, excellent. Yeah. And I think, Bogdan, when you and I have talked in the past, you've also mentioned in developing AI capable drives. So maybe can you talk a little bit about how machine learning can leverage some of these digital twin models, these reduced order models, to optimize drive behavior as we start kind of entering the age of AI?
Well, the AI in our current conception means that we'd like for this process to be capable of learning from the day-to-day experience, and then making decisions about changing the drive behavior. We are thinking of heading for a certain time parallel. One would be the drive will be operating according to scripted algorithms that are provided and stored in the memory of the respective drive. But then in parallel, we are also looking at a way that we can learn from the process and then see if we can find a way to alter the behavior, the original recorded behavior of the drive, and alter that in a way that it both safe and serves the customer needs. So this would be the final purpose of learning from the process, but also in our labs, providing these ROMs with training data, and then allowing it in you could say some artificial manner, but actually related to the process needed by the customer, so that we learn and provide this data. And once we know that it's safe to implement changes, we can do that, and we allow a parallel brain, let's call it, of the drive to make those decisions once it is safe and certain that those decisions will have been validated by what the process is seeing.
Mm-hmm, mm-hmm. Yeah, that sounds really exciting. And sort of along those lines, just maybe looking ahead, what is your vision, long-term vision for digital twins for these medium voltage drives? You think you have things like modeling the full drivetrain with ROMs, like building blocks? Do you have other things you'd like to see? Where do you see this going in the future?
Well, Innomotics has the capabilities with all those R&D departments that are here in the US and in Germany and elsewhere to provide different tasks to different groups. Our group here in the US is for the time being involved with this electromagnetic behavior of the drive. So we have the respective ROMs and this CFD thermal behavior. But other colleagues, for example, in Germany, they are looking at the vibration aspect of the motor, also some of the driven mechanism. We have to keep in mind that the driven mechanisms are very diverse. Sometimes it's a pump, sometimes it's a compressor, sometimes it's a transportation belt, whatever it is different. So we have to involve in this process all those specialists that can extract the essence of those applications, and that they can provide ROMs that we can incorporate into this chain. So looking at how fast IE is moving in the world, I think we are just, maybe 3 to 5 years away from being able to provide this kind of complete control of the drive chain to our customers, and of course extract the financial benefits of being the first to do so.
Awesome, excellent. Thank you so much, Bogdan, for all this information. Talking about how Innomotics is using simulation and digital twins, how you've used ROM technology as well as hybrid digital twins to push medium voltage drive performance. Over the years, we've partnered on a variety of different things, and having you as a customer and a partner has really been fantastic. It's helped us improve our technology, and hopefully we've helped you achieve some of your targets as well. So thank you so much. And to the folks who listen, thank you again. Thank you for the engagement. This is the last episode of season 2. Keep engaging, keep letting us know what topics you'd like to hear about. We're excited about next year and season 3. We have a lot of exciting content coming out, and we're looking forward to connecting with you and talking to you then. Thank you, everyone, and thanks again, Bogdan.
My pleasure.